Next, I've got Drew Wilkerson. He's from York College in Pennsylvania. And he's got, instead of him doing most of the work, he subcontracted to some students, and they're going to show you, show and tell.
We're building radio tele. Well, let me tell you first. I'm Steve Wilkerson, or everybody knows me as Drew. Okay, York College is a small liberal arts college that happens to have an engineering and computer science program. Okay, the engineering and computer science program is very healthy at York College. It's been growing about 15% for 20 years, so it's doing really well. We were asked to build a radio telescope, okay, as a community project-based initiative. We usually do capstones. Our capstone design has to have a design and build something, okay? And in the past, it's always been formula cars, Baja cars, and competition-type events. More recently, the students have shown an initiative that they want to do things that are community-based, where we're putting something back into the community. And that's how this came about through one of our professors and Kerry Smith at the Astronomical Society. He'll tell you that story for sure. So this is the telescope that was out there, okay, and it's going to be replaced by this telescope right here. And the students are going to tell you about this, but I can tell you for sure that we collectively did not have one Jansky of knowledge about radio astronomy prior to this project, okay, if you know what a Jansky is. So with nothing, no more, you guys come on up and we'll get them started. This is AJ Berardi, Willie Ampman, and Dan Shook, okay, and they are about to graduate in 1 week. That's a good, but who's that, right? Look at that foot rester.
So yeah, that's actually the pipe that the radio telescope is going to sit on. So you see how big it is. Crazy. Next slide, please. So design process. So we're going to talk a little bit about the design process first before we get into the details of how it's going to be assembled. So initially we had 32 design ideas. That's because we had a team of 8 engineering students. That was 3 mechanical, so the 3 of us up here, 3 computer engineers, and 2 electrical. So everyone kind of came from a different background, and we all had different ideas, and all contributed very interesting designs. But from there, we all decided on one of our designs that would be tangible. So we had 8, and then we narrowed it down to 2 as a group, 2 good designs. And then from there, we went through the pros and cons of each of those 2 to get one final design. So before we did any of that, we had to decide whether or not we were going to do polar or azimuth. So we have some pros and cons for our specific application. So polar was easier to code. So the electrical and computer guys go, yeah, polar. Like, let's not go into that just yet. We've got to look at everything. It cannot track the sun well, and Kerry wants to stare at it. He wouldn't, sit out there like that if it didn't burn his retinas. But it was a little difficult to design mechanically. Whereas azimuth was easier to build, we could track polar objects and other objects, but we needed an additional motor, but that really wasn't an issue to us. And most of the research that we've done, we found that radio telescopes around our size were as old. So, next slide, please. So design requirements. So we sat down with our customer, Kerry, and the rest of YCAS, and we came up with some specifications. Elevation would have to move about half an RPM. Azimuth would be 2 to 3 RPMs, and those are our acceleration times. So we had kind of like a baseline, what we had to meet, and then a stretch goal. So those are our accelerations for that. And then we had 3 levels of redundancy for our motor stops. So in software, we have proximity sensors. So the telescope, say in elevation, it's coming down, it's going to go towards a sensor, it's going to be, all right, stop. And then if it goes past that for some reason, there's a bug or something, there's a limit switch, and that'll stop it with electrical. It'll cut power. Let's say it's going really fast because Kerry's like, oh, I need to look at that now, and it goes past the limit switch, still cuts power, it's still got inertia, it's going down. We have a bump stop, mechanical. Stop it, then it tracks, and it won't hit the ground, damage the dish, or hit anybody at the park, God forbid. Next slide, please. So this is one of our 2 designs that we narrowed it down to. It's called Bella. It's stands for Ball Screw Elevation Linear Actuator. So this was taking the existing structure that was donated to us. It was designed by SSE. So the original way that it worked was there was a manual jack screw to change elevation. So you have to crank it, and then in azimuth, it was held on it was some type of friction device. It wasn't a bearing, it was like metal contact. And that friction is what held it in place. So you would disengage that lock, and then you'd have to move it by hand. So we decided we could motorize the jack screw, put a linear actuator in that, and have it move up and down, and then drive a shaft through the center, put it on a bearing, spin it that way. And next slide. And this was the other design, fire, for inertia, rotation, and elevation. So this was a counterbalance design. So we would reduce our torque needed. So the way that it works, we have an elevation shaft in the center, and the whole thing kind of rides on that. And it would be motorized. Just right in there, and we apply it this way or that way to change elevation. And then of course we would have a shaft driving the azimuth like that. Next slide. So, and this is the first iteration of our final design. So we took Bella and put it on fire, and from the ashes rose a phoenix. I can't take credit for that. That was Bill that came up with that. He drew up a little cartoon and everything. But so we combined the two. We would have it counterbalanced, and we would have it driven by a linear actuator, because that seemed to be the way to go. And this is kind of like a crude design. We were trying to get the way that would piece together, get our minds thinking about it. We really wanted to work further with it. We didn't have specific dimensions for the SSE parts. So we were using kind of everything up from there, from SSE. That's the hub, and then that's the dish. We're actually missing some pieces on this. That's how crude it was. We're just, all right, here's a dish, here's the hub. That's the basics of what it is.
You probably had it on the previous slide, but what was the spec for the range of azimuth?
The range of azimuth. I didn't have it on there. I think it was
0 to 100 degrees.
azimuth.
I'm sorry, on
360.
but 380.
It's like -2 to 362 for azimuth.
I'm sorry, I'm thinking elevation. Yeah, 370.
370 degrees of azimuth rotation.
Right.
Yeah, next slide. So this was our second iteration. You can see it's starting to look more like a radio telescope. We were in contact with SSE, and we got 2D drawings from them, original drawings of the dish, and then we model all that. So we have ribs, struts, all that is connecting the panels of the dish to the hub. See that here. Then on the back of the hub, we have a hub plate, and welded to that plate will be our shaft that we're rotating on. This is actually the design that we took here to Green Bank last summer, and we spoke to some of the engineers here and said, how does this look? Do you think it's tangible? What do you think? And they came back with some feedback for us. They said mainly these counterbalance arms, that would be a problem, because you're going to have vibration with that, and we don't want it to reach a natural frequency while we think to break. But really, with that, when it's moving, they didn't want it to oscillate as it's trying to stand still. All of our readings will be off carrying set. We don't want that. Next slide, please. Now it's really starting to look like a radio telescope. This is the third iteration, still Phoenix. So in this one, we had truss designs in our counterbalance, so that would eliminate some of the vibrations. The trusses were bolted together, and then from there, we had members coming off the hub that we plan to weld to the hub, and we would bolt straight into that. And again, we have the hub plate and the shaft welded to it. Everything kind of looks more professional, more streamlined. And we even added holes at the bottom of the hub plate for water to drain, because we didn't want it to fill up with water, and then that would increase the load, and maybe the bearings of the shaft wouldn't function properly. And not yet. So since we had everything modeled, we had the full weight, load, and we had our torque requirements. And from there, we were the size of a linear actuator. And the linear actuator that we found we needed was too much money. So we decided to switch to a motor driving the shaft directly there. You have a question right there?
How much is
mean, give me a dollar number.
So we were
Our
on,
entire budget,
Yeah, it was like $10,000.
and at that time, our budget was only $10,000. We got some donations, we got bumped up. At that point, we were over budget, we were like, this is an engineering problem now, so we have to solve it.
The linear actuators we use are under $100. They're stolen from another industry.
Well,
This was
this thing weighs about a ton, and the stroke we needed was
30 inches.
pretty decent.
Yeah, that's the problem with the stroke.
Yeah.
Yeah. Next slide, please. So this, fourth iteration, Phoenix Mark IV. This is the final design, moving in azimuth and elevation. You can see we have a couple changes here, but I'm not going to talk about that. I'll have my team member here, Dan Shook, talk about that. Dan? Next slide.
All right, I'm going to obviously discuss the final design that we came up with.
Dan, move into the screen view.
Stand in the red zone. Is this okay standing over here?
Yep.
Okay. All right, so this is just to give you an overall perspective of the size that we're talking about of the radio telescope. So we put a 6'2" man standing next to it, and you can see that.
Would be 6'2".
Well, that's about my height, so now you can visualize it's about 2 to 3 times me stacked on my shoulders. And the dish itself weighs about 1,200 pounds, because it's an all steel, stamped steel dish. And the whole weight of the whole assembly will be about 2 tons once it's complete. And then the diameter of the dish, you can see, is about 15 feet or 4.5 meters. And the counterbalances alone weigh about 1,200 pounds, just to give you an idea. And I want to give a special shout out to a fellow named Cliff Bates. He did a similar radio telescope project about the same size, and he documented it very well. And that gave us a lot of information on how to proceed with our design going forward. Do you have a question? Next slide, please. So talk about some of the big issues that we ran into with our design. Obviously, the fact that it's such a large project, we're a smaller school, some of the parts we would have to get made outside of it, because we don't have the capacity. We have a really nice machine shop, but it's only so big we can fit on the machining centers. So that was one thing. Now you're talking about, this whole assembly weighs several tons, so you have to think when you're going to install it in the part, how are you going to do that? You have to think of how you're going to rig this thing up once everything's complete. So another issue faced. And then, as AJ kind of alluded to with our parts, the larger parts are going to cost a lot more money. And with limited budgeting, we had to think of that the whole time. Is how can we make this as inexpensive as possible, but also make it the best thing that we can make it. Another thing with a big dish like this, you're going to have significant live loads such as wind, rain, snow, ice. A little diagram here shows you the static loading of about 2 tons for the whole structure. And then we have about 3 tons at a 90-mile-per-hour wind. So obviously, most likely it's not going to see those kind of loadings, but when you're designing something, you always have to design for the worst possible thing because you don't want it to fail in anything it would ever see in its life on Earth. And then, to move several tons of metal, you have to think, you got to put decent-sized bearings, motors, all that kind of stuff. So you have to put a lot of consideration into how this thing's going to pivot on its different axes to make sure that it won't fail and it will be able to pivot smoothly and accurately to be able to position at the sky to receive signals. Another thing, sustainability. This will be outdoors, so you're going to get rain, snow, melting snow, wind, debris. This thing has to be sealed to the outdoors. It has to be able to withstand water getting into the inner electrical components. You also want to make sure that you can replace anything that might need to be replaced. So you want to make sure you don't put this thing together, and if somebody wanted to ever replace a little electrical component, they'd have to move the whole satellite, take it all apart just to do that. And then you also have to think that lubrication, you're going to have pivot points, so you want to make sure that it's really easy to lubricate, because if it's not easy, nobody's ever going to do it, right? And then this represents our college, so we want to make sure that it's a really professional design, it lasts a long time. It also represents YCAS in the local York area and all the businesses involved, so It will be something that everybody can be proud of. And next slide, please. So this is an overview of the main components. The main thing to notice is it's very modular. So what we try to do, because it's like a big structure, is to make it into smaller, somewhat pieces, so that it would be easier to make at the school and local businesses that are helping us. The existing dish that was donated to us, so that was given, that was basically all we had to start with, is the dish. So everything else was left to the imagination, created out of thin air, and with the help of research. And the dish right now is disassembled, so to get it up and running, once we get the structure built, will have to be put together and refinished because it was sitting outside for a while. So there is some work involved in that, but it's a nice starting point when you have something to start from. That will connect to what we call the triangle connector. So that is the connection point to the dish, to the rest of the structure. And you'll notice that that also has the counterbalance weights, which will consist of basically barbell plates that we can, as we're assembling it, put it on to get it perfectly counterbalanced and put more on or less as needed. And that will all pivot for the elevation movement, what we call the elevation frame. And within that frame is a gearbox, which will have a stepper motor, and that will provide the elevation movement. And I'll go into each piece in more detail. And then that will connect to the azimuth, which will turn it in the azimuth direction. And then finally, the post is actually 14 inches in diameter. You saw it in that picture. AJ just showed you, and it weighs, the post alone weighs about 600 pounds. It's a pretty big post. Go to the next page. So connecting to the existing dish. So we went over that. We have the existing dish, and we have the triangle connector. So one thing that was a benefit of this over the last previous design is we're not doing any welding to the existing dish. One worry there was that when you weld something, it's going to distort it. So we want to avoid that. So what we did was we basically took what was given and we figured out a way to connect to it. And then you can see that it's all made of structural steel and weldment basically. So we can cut up smaller pieces, weld it together, and we have our connection point. And it will also incorporate eventually a stowed position lock, which will allow us to lock it in position in the event of like bad weather or something, to keep the dish in a safe position. And up here on the left, you can kind of see the evolution of how, like I said, this was created out of thin air. So, in the beginning, it just started out as like this basic tubular frame device, and it evolved into what you see as our current design. So this is the what I was saying, elevation frame, so the triangle connector and the dish connect to that. And within the elevation frame, you have the elevation gearbox, and that is a 50-to-1 gear reduction. And you can see the shaft runs through it. And the shaft is supported on each end by two Timken spherical roller bearings, which will allow slight shaft misalignment for manufacturing tolerances and stuff. And they're greasable, so maintenance goes into the whole thing. And you'll notice that the slots in the frame itself allow everything to basically be disassembled easily. So if something for some chance would ever have to be replaced, it's pretty easy to do that. And the whole thing is connected by means of compression sleeves. That's the fender drive labeled in the diagram right there. And they basically slide on the shaft and slide into a bore, and then you tighten screws on them, and they expand around each part. And they have significant holding torque. And then you won't have keyways cut into your shaft. So you'll strengthen the whole design by using those. And they're also, you can take them off pretty easily. All right, so once that's done, connects to the azimuth. And the azimuth is kind of like the brains of the whole thing. There was a lot of work that went into that because a lot of stuff was involved in just this part. So the main component is the slewing ring, which they use in bucket trucks and excavators to rotate on. And the nice thing, it's kind of like a giant bearing, but on the inner race, you can get them with gear teeth. So it not only gives you a way to rotate the whole thing, but it also gives you a driving mechanism because now you have a gear. So that is driven by a right angle gearbox, which is a 100-to-1 gear ratio. So the nice thing is we can use the same stepper motor for the azimuth and elevation movements, which goes into the maintainability, because now if you need to replace something, you can use the same exact component on either one. And also within this, you'll see that we have an encoder, a ring encoder, which will give us really accurate position feedback, so we'll always know where we're at. And then I'll go into this a little more on the next slide. Also within this is stops. So we had, like AJ was talking about, redundancy. We had limit switches to cut electrical power and a hard bump stop. And the hard thing about that switch is how do you design a switch that allows 0 to 360 degrees of travel. And I'll show you that in the next slide. So this is kind of a blown up view if you're looking down on the azimuth. And if you look at the right, around the outside there are 3 proximity sensors, each at 60 degrees. What these do is they give you kind of a check. So, you know, if the encoder is giving you feedback, you have that kind of proximity sensor feedback to make sure that you're in the right position. And it also tells you by going over 2 proximity sensors, you know what direction you're turning in. So you can always check your software to make sure that you're going where it says it's going. And then right there on the right is kind of the, it's an incorporated hard stop and limit switch built into one. If you want to play that video on. So as this thing rotates, this bar right here actually extends down into the cavity. You can't really see it in this picture, but you can see that it contacts that pivot bar. And on the end of the pivot bar is a cam action, and it will trip those limit switches at -2 degrees and all the way over to 362 degrees. And the nice thing about that is once it trips electrical power, it provides another 2 degrees of travel before it actually contacts a hard physical stop. So it gives you a little bit of time once it cuts electrical power to allow it to drift into that position. So that was one of the challenging things about the azimuth design is, you know, coming up with a way to spin 360 degrees, well, a little over and under, and also allow limit switches to be incorporated in it and a hard stop. And finally, working down the design, we have the post, which connects to the foundation. And luckily, we contacted our civil engineering professor, and he set us up with 2 local York companies who provided enormous help on this, because we're mechanical, we design the steel and all that, but to connect to the ground is a whole other science in itself. That's something that we didn't want to tackle too much because we had so many other things to do. So what we did was we devised wind loadings, you know, all those live loads I talked about, and once we came up with all those, we had something to give to them to say, we need a foundation to withstand these loadings. And so GTA, they were kind of a geotechnical part of the engineering. What they did was they went to the site, pro bono, drilled down into the soil, and they determined what the makeup was. And what this does is it gives you a bearing capacity for the soil. They can pass this on to Carney Engineering, who actually designs the foundation based on their information on the soil and also based on the loading. So now we have our foundation fully designed, and Billy's going to go into kind of where we're at and talk about the progress made so far on this huge project.
Yes.
How much concrete is in that foundation?
I don't know off the top of my head, do you?
No, I don't know either, but that'll be put in soon. They're getting ready to.
It's many cement trucks full.
Yes.
It's a 6
Yeah,
by
it's
I
a
think it's
pretty
a
big.
foot deep.
Probably a cement truck full.
6 by 6 foot
And
slab.
I think they have to use special concrete in some place, or, you know, it has to have wire mesh in it and all kinds of things. But it was all designed by a civil engineer that had a professional engineer's license, so.
It was a 10-foot square base with a pillar in the center, all rebar.
Yeah.
It's pretty big.
Sounds awfully familiar.
All right, so yeah, I'm going to talk about the progress we actually made with it, then starting back from the ground up. This is the post we have. It was donated by Lally Pipe and Tube in Ohio. We actually have Boyd Hydro and Wolf Tooling machining it right now. And the machining work and welding has been done on it. It just has to be sandblasted and sent out to be painted. The current Capstone team is working on that.
Just, what was the price of shipping this?
The price was about $400.
So we're hemorrhaging money as we're doing this, just to get a free pipe, $400 to get it there.
And that took 2
This is
weeks.
the pipe, is that the pipe you were standing on, the
Yes.
first
Yeah.
slide?
Yeah.
That's it. All right, sorry.
So this is the azimuth base plate and gearbox. So everything, the dish, the gearboxes, the motors, the elevation frame, counterbalances sits on top of that plate. And so we don't want to disassemble it to fix out a limit switch or something. So there's access ports that were put in. And then the motor and gearbox have been integrated into the actual slew ring. And it's sitting on a mock flange, so it's not the final components. We were able to modularly test it as we went along. So this is our test part that lets us test each component as we complete it. Then there's the backlash adjustment. So this is, in the middle is the actual flange that provides a flat surface for the bearing to sit in, so there's no distortion, it doesn't ruin the lifespan of the bearing. And then the sensor plate is in the center with the hard stop, as you can see. And then the gears mesh perfectly, give us the desired motion. It goes full 362 each direction. Slide. And then this is a close-up view of the actual hard stop mechanism. So the previous picture, it's labeled A is the plate and bearing. B is the actual hard stop mechanism, or the pin that goes in. C is the bumpers. D, the bumper contact. And then you can see how it touches the limit switches as it goes past, so it doesn't actually, it has the software stop before the hard stop. Then X is just the pivot point for that lever action.
Somebody's sneakers on.
Hmm.
Somebody's feet is underneath.
That's Dan's statement.
No, it actually is.
So, working through the project, we ran into time being a big issue. And there's semester breaks where we're not on campus, and semester's only 14 weeks, but it's really only like 13 weeks. So we knew we wouldn't finish the whole thing before the end of the semester, but we wanted to be able to demonstrate both systems, the full drive system working together, the as-L. So our solution to doing it right, so we don't machine the elevation frame right there first and then weld it and distort it so nothing is, or everything's misaligned. We built a wooden prototype elevation frame that's a 1-to-1 scale that sits on top of the base plate. And then go to the next slide. This allowed us to actually mount the elevation gearbox on top of it and put the shaft through, mount the bearings. So that showed, and then we could test it together, and they both work as one system to move in a as-L coordinate system that's fully integrated. And then on the next slide, okay, so first is the electrical test bed. No, that's fine. The electrical test bed, that provides two 48-volt direct current power supplies for the stepper motors, and then one 24-volt direct current for the control system, which the control system consists of two safety relays, the PLC controller, Ethernet switch, and the motor control unit that controls the entire system. And this will be mounted onto the actual base of the telescope. So this is kind of where we ended off. We had Carrie donate 3-foot dish, and we put it on some mock counterbalance arms so we could actually see dish movement. So it's a small scale test, I think about fourth the actual size around that. And then eventually we could put a receiver in this, test data acquisition and the database integration of the whole system to test out the control software. But then we're going to work on getting the current Capstone team is going to work on getting the triangle assembly together so that they can actually put full 2,200 pounds on and do a full stress test. I don't know if it'll be on that test cart because there might be some clearance issues, but on a test cart version before we actually put it together in the cart.
And just to give you an idea of the cost, the metal, they just ordered the metal for this. This was $1,000 in metal. I mean, then we have to get professional welders to weld this.
Yeah.
And then we have to have it machined. So there are some costs in this. Sorry.
And then on the next slide, this is, if you want to play, this is a video of the first time that it's actually being driven by the control software. So that's one of the computer engineers, and then another computer engineer in the back, or in the front row. Then Travis reaches for the e-stop, just in case, but we didn't need to use it. This was, actually, you can see they're wearing the shirts we're wearing now, because this was about 15 minutes before our final presentation that we got to work the first time. So we were pretty proud of this moment, because it was the full drive system working as one unit controlled by the control software. They put in an as-L coordinate and it went to that position. It knew where it was. The only thing missing is the receiver.
So you got a passing grade?
Yeah, we did. With honors. Otherwise, we'd still be up there working on it. You go to the next slide. And then one of the other things that the computer engineers and computer scientists worked on is it was 3 computer engineers, but then about 14 computer scientists as well working on the website and everything. They made a VR simulation of the actual observatory. So all the way on the right is the current YCAS observatory, where they have the optical telescopes. And then the blue building in the middle, that's the control room for the satellite dish. And then that's the actual radio telescope right there.
I think our telescope actually sits a little higher than this, doesn't it?
Yeah, I think the scaling was a little bit off in this image.
Yeah.
But yeah, it'll
So it's sitting higher, it's above that sense.
Yeah. Yeah.
The perimeters.
And this is just another view of the telescope. That one you can see it's a little higher up on the left, more detailed view of the actual VR telescope. So if you go in the VR goggles, you can actually, that's what you'll see on the left side. And then we're also going to have AR goggles, which allows you to visualize it in the room or wherever you are and go through the components, and eventually you can simulate the data acquisition and see what was actually collected through a visualization software. First we got to get it to run. Next slide. So this is a top-down view. The black squares broken into quadrants, that's just a point where someone can stand in VR, like a point of interest. It's not going to be there. But on the right is the actual observatory, and on the left is the dish. And if you click ahead, it's superimposed on Google Maps image, showing you actually like where in physical space on the Earth this will be, and more or less about the size. I think it's a little bit bigger, the telescope, but you can see where it will be. There's a nice open field where you can actually observe the night sky and the day sky, since it's radio telescopes. Next slide. So yeah, this is going to be an access point for radio astronomy in York, PA. It can provide educational outreach, research opportunities for schools and universities, as well as amateur radio astronomers that want to assign some data acquisition, some observation that they know about. And it'll broaden the cosmic perspective in York, PA, which there was a 12-foot dish, but it didn't work, and now this one will replace it. And if nothing else, maybe we'll get free satellite TV from it. That's our presentation.
Did you do anything with the ground in order to enhance or control the interaction of antenna with the ground?
On the foundation?
The ground around the antenna, so that
No, I'm going to, yes,
We did.
No, we didn't do anything. We just designed, or had the foundation designed.
That might be a Carrie
Yeah,
question.
I don't think there was
That might
anything.
be-
I couldn't hear it.
Something about the ground around the dish?
You mean like for seismic activity or anything?
No, I think he was talking about reflectivity and those things. So there's actually a flux at the ground that people worry about, right?
Okay.
Yeah.
Well, you're not planning to transfer, is that correct?
Not that-
Carrie, that's a Carrie
Well,
question.
it's, if you're talking about the conductivity of the ground, then that has not really been investigated. I mean, it's just ordinary soil. I mean, it's,
A lot of rocks out
Yeah, I know.
no, it's,
The foundation is going to be covered with gravel, right?
No, it's not, conductivity is not relevant.
yeah.
there. Right.
Is it undisturbed ground, in other words, original
It's been there for decades,
foundation?
Eons.
So
It's been there for
not built-
decades.
You're not building on fill of any kind?
No.
No.
Yeah, that's important.
Do you have a map of the environment for electromagnetic radiation emissions for human exposure near the telescope?
We're not transmitting, but it's a good question. Yes, we did a spectral survey of the area. It is polluted around the
But
public
it'd be
service.
wise to get meters and to create a map of the different positions, you know, what the electromagnetic radiation, I'm harmed by electromagnetic
They're not
radiation. I can
transmitting.
detect it as real.
If
They're
we
not
were,
transmitting.
if we were emitting electromagnetic energy, I would understand your concern, but I'm not sure I totally.
So this telescope is not
Is
emitting,
receive
it's
only,
only
receive
receiving.
only, yeah.
Still be wise to measure the environment, because even though it's receiving, some of the satellite dishes, which are only receiving, I can detect them and they harm me. So I'm suspecting that the satellite, you know, it's reflecting. I don't understand, but I just know that there's something real in the environment that's a problem.
Definitely have to consider that. You had a question, sir?
When do you guys graduate?
1 week. Next Saturday.
Finish it.
The current Capstone scheme.
If I might speak to that for just a moment, I have 5 new students, okay, and to replace these 3, we got 5, which is a good thing, okay, and we're working right now, the pipe, the stanchion, is either complete or almost complete. The elevation mount is about to go out to the shop to be welded and machined, okay? And then the last piece that we'll be building, they ordered the materials to be cut for the counterbalance, which they call the triangle, but I call it the counterbalance. So my priority this fall is going to be getting that pipe mounted at the park, working with Carrie and the astronomy place and the new students.
What challenges do they face? Sounds like these guys did all the hard work.
So yeah, they also have to design and build. So one of the things that they did is they went back and looked at the designs that they did. There are some small modifications to these designs, and they're ongoing as we move forward.
All right.
What do you think your pointing accuracy is going to be from the mechanical point of view? In other words, repeatability and slop of the gears.
We had talked about 1/10 of a degree with the encoders.
Yeah, it'll be pretty good, because we have an encoder right after the backlash, so we'll be able to tell absolute location of the actual blast.
That's why I asked the question the way I did, in terms of mechanical stability and slop in the gears, not what the encoder shows.
Oh, through mechanical? Oh, okay.
The encoders will detect the slots.
It will be whatever the backlash of the gear is, which is going to be probably, I mean, I don't know off the top of my head, because the slewing ring is adjustable backlash. So you can adjust that as fine as you want. So it'll be minimal. But the reason why we mitigated that by adding in an absolute encoder to the center of that is to avoid that problem. So the software will basically account for any discrepancies, and it will always be at the right location within the accuracy of the encoder itself. So there'll always be
The
backlash.
encoders don't compensate for slop.
No, but the way the machines work is like, if there is slop, the software will travel an extra little bit to compensate for that. So that's, the encoder will verify that slop, and what will happen is the software will say, well, I need to go a little bit more, so the gear will turn that little bit more to.
The encoder reader is stationary, so if there's slop, the encoder, that will be recorded on the encoder.
Yeah.
Okay? So
Okay, so there's no mechanical gears or anything else between the encoder and the parts you're moving. Is
Exactly.
that true?
Exactly.
Right. Yes.
I'm getting at the point where you wind up trying to use the encoder feedback to compensate for mechanical slop as, say, the wind changes. And
You can do that,
and you wind up oscillating within the gap of the slot.
Yeah, but like I said, that's an adjustable gap, so you can get it down to the point where it'll be negligible, to the point where you probably can set it in your software, a limit or a range to prevent it from moving if it's within a certain, negligible amount, so that you won't get that effect.
The gearing's also 500 to 1. You have a lot of control over it.
Yeah.
What's your mean width at your chosen frequency?
It's about 1 degree, 1.5 degrees.
Yeah, so a tenth of a degree is meaningless then.
Maybe 1420?
14.
Just curious in general, specifically about this project in general, what about lightning protection?
That has been considered.
It will get hit.
Yeah, but that's not my
I think it's pretty tall.
answer is
He's pretty tall, I think
This guy has a
would
question.
make use of him.
Of mechanical design and motorized tracking and this 50-inch diameter?
15
feet.
50 feet diameter. And I don't know about the surface of the dish, but what's the target in the radio astronomy? What do you want to observe? What's the plan for that area?
Well, okay, so we have a spectroside receiver from Radio Astronomy Supplies. And our initial work will be to do solar work first. Then we'll eventually break into, looking at Sagittarius A. We want to see, since we can do spectral, we want to look at the Doppler shift on the arms. Again, it's a semi-research instrument, but the real mission behind this whole project is to do educational outreach. So the fact and you'll hear about this this afternoon when I talk about how this all came together, the fact that they said we're going to make this fully trackable and fully steerable, now we can start talking about pulsar work. And that's really intriguing to us, because for me, that's the holy grail for me, is the we can detect a pulsar. That's going to be really, really neat. But again, it's really to spin people up. It's amazing. Every time we have a public star watch, I'll have my IVT out, and I'm pitching radio astronomy while these guys are doing the optical. And it's amazing the questions that come back, and we never heard of anybody even doing this kind of thing. So and we know from experience, there's a lot of optical, amateur observatories that don't do radio astronomy. And when they get their first exposure to it, it's a wow factor. And I suggest that when you have some free time, these guys put together an awesome poster that Todd and myself had gone to Gettysburg for a conference, and we had a poster time to show and brag about our project. So they put a lot of time in the overview of the whole project, which it's hung on the wall out here now. So you'll hear more of my talk. Mine's more of the historical account of the whole project, including Eric's Sauter's science project, how we got this. Todd is going to talk more about the software development and the real mission behind the whole project. So you'll get part 2 this afternoon, but that's basically what we want to do, Chip, is to get the word out and get people on board as to what radio astronomy is all about, and to have fun with it. It's the whole idea.
What size concrete block did you use to mount the post?
It's a 10 foot by 10 foot slab base foundation. 10 foot by 10 foot slab base foundation buried in the ground with a pure
Rebar enforced, yeah.
It'd be pretty big.
Is there any opportunity for SARA to be involved in this project and perhaps contribute?
Yes.
Absolutely.
The answer is yes.
Yes.
Okay.
Large denominations appreciate
But I just wanted to
We
mention
were really
that.
excited when you said, Skip said he wanted to be involved with that.
Oh,
Immediately,
well, Skip's
got
doing
me.
it, we don't need to.
Well, he's part of
Yeah, because
SARA.
he has all the money since he's not. No, he doesn't have the money. That's right. negotiating policy. We have the money. You have the money.
But anybody else that wants to be involved, please, before I leave, let's make the
Talk to
contacts.
us, yeah.
The 5 new victims will be here next year.
That's the plan. The plan next year is to come and brag about about all the great work that
That we're up
Carrie's
and
doing
running.
with pulsars. So we'll see.
I don't think we'll be ready for pulsars, but we expect that first slate in May or June.
Yeah.
2020. Excellent.
Pretty awesome, guys, pretty awesome.
Thanks, Jeff. Lunch is happening soon, very soon, like now, but.